Hello everyone, and welcome to the Waveshare ESP-32 Getting Started tutorial. In previous lessons, our code ran inside a single app main function, using a loop to handle tasks, which is similar to the Arduino approach. This works well for single-purpose applications, but in real-world projects, the ESP-32 often needs to handle multiple tasks simultaneously, such as reading sensor data, communicating with the cloud, and updating a display. If we use a traditional sequential execution model, the program processes each module one after another in a fixed order. This super loop approach has several clear drawbacks. If one stage takes too long, the entire loop gets blocked. As subsystems are added, the loop cycle becomes longer and response time degrades. Passing data efficiently between different modules becomes difficult. To implement multitasking efficiently, we need a real-time operating system. ESP-IDF includes FreeRTOS as its real-time operating system. FreeRTOS is one of the core components of ESP-IDF. Virtually all ESP-IDF applications are built on top of it. In this lesson, we'll introduce the basic concepts and usage of FreeRTOS on the ESP-32, helping you understand the fundamentals of multitasking programming. First, let's understand what FreeRTOS is. FreeRTOS is an open-source real-time operating system kernel designed specifically for embedded systems. It provides operating system features like task scheduling, inter-task communication, and synchronization for microcontrollers. It is integrated into ESP-IDF as a component and serves as the runtime foundation for the entire framework. One important note, ESP-IDF does not use native FreeRTOS directly. Instead, it is a customized implementation based on an earlier version of FreeRTOS. The main modifications include adding symmetric multiprocessing support for dual-core chips, as well as hardware adaptations for ESP devices. As a result, its kernel behavior and some APIs differ from official FreeRTOS. This customized version is commonly referred to as ESP-IDF FreeRTOS. Currently, native FreeRTOS already supports SMP, and ESP-IDF may gradually migrate to the official FreeRTOS in the future. Before diving into multitasking, we need to clarify one key point. A single CPU core can only execute one instruction at a time. Multitasking is achieved by having the scheduler rapidly switch the CPU between different tasks. Because the switching happens so quickly, it creates the illusion that multiple tasks are running simultaneously. This is commonly referred to as concurrency. On a dual-core chip like the ESP-32, however, things are different. The ESP-32 has two CPU cores and supports symmetric multiprocessing, which means two cores can execute different tasks truly in parallel. That is, two tasks can run on different cores at the exact same time. To summarize, the key features of ESP-IDF FreeRTOS on the ESP-32 include multitasking scheduling with real-time support, symmetric multiprocessing support, making full use of the ESP-32's dual-core architecture, optimizations specific to ESP hardware. Next, let's look at the core concept in FreeRTOS, the task. A task is the most basic unit of execution in FreeRTOS, similar to a thread in a general-purpose operating system. Each task is an independent C function with its own stack space and execution context, and typically contains an infinite loop. Unlike traditional microcontroller programs, which typically consist of a single main function with a large loop that processes various tasks sequentially, FreeRTOS allows us to create multiple tasks, each responsible for one specific job. These tasks are scheduled by the FreeRTOS kernel, which decides which task gets CPU execution time at any given moment. A task can be in one of four states during its lifecycle: running, currently being executed by the CPU, ready to run, but the CPU is busy with another task, blocked, waiting for an event, such as a delay or peripheral response. During this time, it does not consume CPU time. Suspended, blocked indefinitely until resumed by another task. So how does FreeRTOS decide which task to run? On a single core system, the scheduler follows three core principles. Fixed priority, always selects the highest priority task that is ready to run. Time slicing. When multiple tasks at the same highest priority are ready, they run in round-robin order. Preemptive scheduling. When a higher priority task becomes ready, the scheduler immediately switches to it. On dual-core chips like the ESP-32, things get more complex. IDF FreeRTOS also considers core affinity. Each task can be assigned to run on a specific core or either core. Multi-core coordination, ensuring tasks are properly distributed and synchronized across cores. With the basics covered, let's make this concrete with an example. This example creates two tasks. Task B will suspend itself after running for a while, and Task A will resume Task B at a certain point. Task B will then delete itself when a condition is met. Through this example, we can directly observe task suspension, resumption, and deletion, and understand the complete life cycle of a task. First, create a new ESP-IDF project. Then, copy the example code from the tutorial document into main.c. Let me walk you through the key parts of this code. These two headers provide the core FreeRTOS functionality and task management APIs. Task handle T is the handle type used in FreeRTOS to identify tasks. We define two global handle variables so that one task can operate on another via its handle. Now let's look at Task A. Task A prints a count every second. When the count reaches 10, it resumes the suspended Task B. Note that vTaskDelete, PDMS to ticks 1000, here puts the task into the blocked state for 1000 milliseconds. During this time, the CPU can execute other tasks. This is an important concept in multitasking programming, voluntarily yielding CPU time instead of using busy wait loops. Now let's look at Task B. Task B also counts and prints every second. When the count reaches 5, it calls vTaskSuspend to suspend itself. The parameter null indicates that the operation applies to the current task itself. Once suspended, Task B will no longer be scheduled by the scheduler until another task calls vTaskResume to resume it. After being resumed, Task B continues execution from where it left off. When the count reaches 10, Task B calls vTaskDelete to delete itself. Note that RTOS task functions should not return. If a task needs to exit, it must call vTaskDelete to terminate properly. Inside @main, we use xTaskCreatePinnedToCore to create the two tasks. This is the IDF FreeRTOS task creation function that lets you specify which CPU core a task runs on. Task A is pinned to core 0. Task B is pinned to core 1. Both tasks have the same priority, 10. Each task gets a 4096-byte stack. As a side note, @main itself is also called from within a FreeRTOS task. When @main returns, that task is automatically cleaned up and does not affect the other tasks we created. Now click the Build, Flash, and Monitor button to compile and flash the program and observe the output. You'll see, initially, both tasks run in parallel, alternating print messages. When Task B's count reaches 5, it suspends itself, and only Task A continues running. When Task A's count reaches 10, it resumes Task B, and we see Task B continue from count 6. After resuming, Task B keeps counting and deletes itself when it reaches 10. Finally, only Task A remains running. Note that in a multitasking environment, printf output may be interleaved. This is normal behavior. That wraps up this example. FreeRTOS can do a lot more than this. If you'd like to dive deeper into FreeRTOS and ESP-IDF, check the reference links at the bottom of the tutorial document. We recommend watching the keynote presentation from the 2022 Expressive Developer Conference. Well, that's it for this lesson. Today we covered the basic concepts of FreeRTOS and its role in ESP-IDF, task states and scheduling mechanisms, how to create and manage multiple tasks on the dual-core ESP32, basic inter-task operations, suspend, resume, and delete. In the next lesson, we'll learn how to drive peripherals, including GPIO control, PWM output, and more. Thank you for watching. If you found this video helpful, please like and subscribe to support us. See you in the next lesson.